Hello everyone, myself Dashanas. I'm pursuing my studies at Sri Venkateswara College of Engineering. Today I'm here to explain on the topic based on cybersecurity test bed for smart contracts. Here in this cybersecurity test bed for smart contracts, we are going to explain about the topic that is blockchain and smart contracts and revolutionizing industries, but their security is paramount. This presentation explores the critical role of cryptography in safeguarding these emerging technologies, which is against vulnerability and attacks. So here is the assignment which has been given from our college to make a topic based on the cybersecurity test based on the bed for smart contracts. So let's start with the topic that is the importance of cryptography in blockchain and smart contract securities. That is, here are three types of importance in the cryptography that is in blockchain, that is foundation of trust, decentralized assurance, and that is confidentially protection. So for this cryptography, there are three types of contract securities. That is, cryptography is the bedrock of the blockchain, enabling security transactions and tamper-proof smart contracts. Second is a decentralized assurance, that is, the cryptographic protocols ensures that the integrity and transparency of blockchain-based systems without a central authority. Third comes that is the confidentiality protection, that is encryption safeguards sensitive data and transactions with the blockchain ecosystems. That is the cryptographic vulnerabilities in smart contracts. There are three cryptographic vulnerabilities in smart contracts. That is, first one is arithmetic errors, second one is entrancy attacks, and third is insecure random number generations. In these arithmetic errors, that is, the incorrect implementations of arithmetic operations can lead to overflow, that is, underflow, and also exploitable issues. Second is the re-entrancy attacks, that is, malicious attackers can repeatedly call the contract's functions before the state is updated, that is, draining funds. Third will be the insecure random number generation, that is, this flaws in generating random numbers can compromise the fairness and security of smart contracts applications. Insecure arithmetic operations and re-entrancy attacks. So what are the insecurities in these arithmetic operations and what are the re-entrancy attacks should be done for this cryptography overflow or underflow, that is re-entrancy, or to get vulnerability through this. In this there are three types of attacks we can do through this into to the insecure arithmetic, that is overflow or underflow. So improper handling of integer arithmetic can leads to unified states changes and fund manipulations. Second is a re-entrancy vulnerability, that is the falling to update contract state before external calls can allow attackers to repeatedly drain funds. Next is the mitigation techniques, that is using open ziplines, safe math library, and following established security patterns can prevent these attacks. Next topic, that is the cross-chain cryptographic issues. So here in this cross-chain cryptographic issues, that is interoperability challenges, that is securely transferring assets and data between disparate blockchain networks requires robust cross-chain cryptography. That next is the conscientious differences, that is differences in conscientious mechanisms and trust assumptions across chain can introduce security vulnerabilities. Third is the oracle manipulations, that is the compromised oracles can feed false data to smart contracts leading to incorrect cross-chain transactions. Best practices for mitigating cryptographic vulnerabilities. That is rigorous auditing, that is the comprehensive code review and security audits to identify and address vulnerabilities. Second is the extensive testing, in this through until integration and end-to-end testing to validate the security of smart contracts. Third is the formal verification, that is the applying formal methods to mathematically prove the correctness and security of smartness contracts. So here are the best practices that are mitigating for cryptographic vulnerabilities. There are three types of practices that we do rigorously in order to get cryptographic vulnerabilities. That is rigorous auditing. Second is extensive testing, and there is a formal verification. These three has to be done for the cryptographic in this cryptographic vulnerabilities to mitigate the problems and to get the best practices for this. So after mitigating the problems in this cryptography, now it's time to secure the coding standards for smart contracts. So they how to secure the secure coding standards through this smart contracts. That is, we have to do input validations. So through this input validation, we can be able to validate and sanitize all users to prevent injection attacks. Next will be the access controls. So everything needs to be controlled through this accesses. So implementing role-based accesses management in order to resist and unauthorized accesses to critical functions. So we can give two-step verifications. We can give many more through this, which can access control through the owner, and there will be error handling too. In this error handling, gracefully handle and log errors to prevent. So if there are any log errors, we can be able to secure the coding standards from this smart contracts. We can be able to remove those accesses and deny on these services based on the secure coding standards of how we give the input validations and access controls and how to make the error handling perfect. So some basic ways how to make the cryptographic techniques for enhancing how to make it contract security. So these are the techniques which we have seen through this how to prevent the secure or prevent the cryptographic techniques. Now it's time to enhance how to make the smart contract security. In this encryption that is protects sensitive data and transactions with robust encryption algorithms. Using this protect sensitive data and transactions with robust encryption algorithms, we can do encryptions. In this digital signatures, we will be able to ensure that the authenticity and integrity of smart contracts integrations. And there is a zero knowledge probes that will be able to enable private computations and verifiable claims without revealing sensitive informations. And next is the secure random number generation. That is, we can be able to generate unbiased, unpredictable random number to how to enhance the smart contract applications to bake secure random number generations through this. Thank you.